So here we have a proof by mathematical induction question, and it's applied to a series. Now it works brilliantly for series proofs, just because you think of this nature of this domino effect. Well, that's exactly what series are. You have n equals 1, n equals 2, n equals 3, and so on. And if you can knock all those dominoes over, it's a really, really natural way to prove things. So we need to prove that the sum from I equals 1 to I equals n of I squared, so that means 1 squared plus 2 squared plus 3 squared plus 4 squared and so on, all the way up to n squared. Prove that that equals n times n plus 1 times 2n plus 1, all of that over 6 for all integer positive n. So that's what I was talking about for a series. Remember, a series has this natural domain, integer positive n. Right, and this particular formula, actually you will use it again. You'll use it when we come to some of the heavy calculus stuff, thinking of Riemann sums in particular. You will use this. It is a genuinely important result. Right, so we're going to prove this. We'll set it out in the normal way, formal way. So firstly, say what you're trying to prove. So the proposition we're trying to prove, Pn, which is, now I'm not going to write it in the series notation, I'm going to write it kind of in interpreted series notation. So remember what I said, that it's going to be 1 squared plus 2 squared plus 3 squared, 1 squared plus 2 squared plus 3 squared plus dot dot dot, all the way up to n squared equals n plus 1, 2n plus 1, and all of that over 6 for all integer or positive integer n. Right, so this is what we're trying to prove. We need to say that we're going to prove it and how we're going to prove it. So we're going to do a proof, and we're going to do it by the principle of mathematical induction. Right, well, it's a very sort of structured process. You start with this base case. Now, this is for all positive integer n, so the natural base case to use is n equals 1. So we start with thinking, well, what if n equaled 1? What would happen then? So if n equals 1, well, you've got kind of this thing on the left. We need to show that the left-hand side equals the right-hand side. So if you just think of the original notation, it was this sum from I equals 1 to I equals n of I squared. So this is on the left hand side, literally just I squared, or 1 squared, sorry. 1 squared, does that equal, well, this would be 1 times 1 plus 1, 1 plus 1, and then 2 times 1 plus 1. Are these two equal? Well, 1 squared is 1. This is 1 times 2 times 2 times 1 is 2 plus 3. So plus 1 is 3. So this is 1, 2, 3 over 6. And this is 1. Does the 1 equal 6 over 6? Yes. 1 equals 1, which means that P1 is true. So the proposition is true when n equals 1, P1. Right, so now the second step is to assume that the case is true, as in the present case. So if pk is true, if that is true, then 1 squared plus 2 squared plus 3 squared plus dot 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 all the way up to k squared, 1 squared plus 2 squared plus 3 squared plus dot 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 all the way up to k squared. Well, if this is true, then that will equal k plus 1, 2k plus 1 over 6. k plus 1, 2k plus 1 over 6. Right, so now the next step is to find an expression for the k plus 1th case. But it's for something like this, I would very much recommend having a target in mind. You need to know what you're actually aiming at. So I'm just going to put this over here. Target. Otherwise, you can really just get lost and even sort of forget what you're trying to achieve. So the target for our k+1 expression is going to be this, but wherever you see an n, you write k+1. You can use a bracket if you need to. So it's going to be k+1. The n becomes k+1. The n plus 1 it becomes k+1 plus 1. And I won't use a bracket there, but I could. And then this is going to be 2k+1 plus 1. k+1 plus 1. So it's all of that over 6. That is what we're looking to show once we do all this manipulation on it. So now we can write our expression for pk plus 1. So pk plus 1, well, let's just start off simple, as in left hand side started 1 squared plus 2 squared plus 3 squared plus dot dot dot, and it's got to go all the way up to k squared plus k plus 1 squared equals 1 squared plus 2 squared plus 3 squared plus dot 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 plus k squared plus k plus 1 squared, like that, right? Now what we can do, we can use our assumption, because we've assumed that pk is true. So if you look what this was 1 squared plus 2 squared plus 3 squared all the way up to k squared, and we've assumed that that equals this, so we can use that result. So all of this up to the k squared, well, we can use that result. Well, that is k plus 1 equals k plus 1, 2k plus 1 over 6 plus, and then you've just got the k plus 1 squared. Okay, so now we have to work on this expression and try and turn it into the target, right? So if you look at what it's got, so there's kind of a k plus 1 here. Other stuff is going to need some work, but we've got this over 6, which is what we do want. So we definitely want a fraction with the denominator of 6. If I take this k plus 1, I want to find a way to add these, because there's only things being multiplied together on the top. There's certainly not going to be one lot of terms being multiplied plus another. We've got to bring these together. The only way we're going to add these is if we make a common denominator of 6. So the way we do that, times this by 6 over 6. So that is going to be equals k plus 1, 2k plus 1 plus, and this is k plus 1, or 6, sorry, 6 k plus 1 squared, and I'm going to write that as k plus 1, and you'll see why in a minute, all over 6, right? So now we've got our common denominator bit. So I could have done another line, as in said, well, it's this over 6 plus this over 6, but I am a bit tight for space. So now what you can do, we want to find the easiest way to get this in a form that we can really wrestle with it. And if you look at these, so you've got two terms here. They're quite complicated terms, but they are two terms on the top in the numerator. You've got the k plus 1, 2k plus 1, and you've got the 6k plus 1, k plus 1. Now these two terms have a common factor of k plus 1, and k plus 1 is one of the things that's in our target. So I'm gonna pull that out. So equals k plus 1. We're pulling that out as a common factor, and we open the bracket up. Now if you think, well, in this case, if we take this k plus 1 out of this first term, it's left the k and the 2k plus 1. What I'm going to do is multiply those together. So that would be 2k squared plus k. 2k squared plus k. Right, I'm going to leave that open because I still need to pull one of the k plus 1s out of this. So what would be left once we take the k plus 1 out of this term here? And you can think of this as you need to divide this whole expression or term by k plus 1. It's going to leave a 6k plus 1, which is 6k plus 6. It's all positive. Plus 6k plus 6, like that. All over 6, right? Okay, so now just looking at this second bracket, we can call this 2k squared plus 7k plus 6 equals k plus 1. 2k squared plus 7k plus 6 all over 6. So then we're looking to factorize this, and whatever your method of factorizing is, you should find that that factorizes to k plus 2, 2k plus 3. So this is going to equal k plus 1, k plus 2, and 2k plus 3 over 6. So now remember what our target is, which is really quite handy, it's still written up here. We're looking for k plus 1, k plus 1 plus 1, well k plus 2 could be written as k plus 1 plus 1, and then 2 bracket k plus 1 plus 1. Well, 2 bracket k plus 1 is 2k plus 2, and then if you add on the 1, well that's going to give you the 2k plus 3. So let's write this equals k plus 1, k plus 1 plus 1, 2k plus 1 plus 1 over 6. And that is what we were aiming at. So that shows us that the proposition k plus 1, or the k plus 1th case, is true whenever the kth place is true. The kth case is true. So now we finish it off. Since, and remember what we started on, we said n was 1 was the base case. So since p1 is true and p k plus 1 is true whenever pk is true. So since that's all true, Pn is true. You need to say what it's true for all, and it was positive integer n, who's, remember, it was it's a series, and that's the natural domain of a series anyway. For all positive integer n, and this is because of the principle of mathematical induction. Okay, so what you do, you say what you want to prove, your proposition that you're trying to prove. You say, I'm going to prove this by induction. You start your base case, which is usually when n equals 0 or n equals 1. It was 1 in this case. Then you assume that the kth case is true. So that allows you to get an expression. Then you write an expression for the k plus 1th case. And you have a target in mind what you're aiming at. That's not necessary, I mean absolutely necessary, but I think it's a very good idea. And then you work on your k plus 1th statement, having used your assumption from the kth case to make it a lot easier, and then you just keep working on it algebraically until you get to the target. And then you need to write this statement at the end to sum things up, otherwise you haven't finished the proof.